Hey, have you ever wondered how we can truly trust machine learning systems, especially given how complex and unpredictable they can be?
Absolutely. The whole black box nature of machine learning models always gets me thinking. Even if you understand the inputs and the model's structure, it's almost impossible to figure out how it arrives at specific outputs.
Yeah, and that's exactly what the issue is. These models, particularly the deep neural networks, are just so complex because they rely on numerous parameters and computations. Their whole decision making processes are hidden under many layers of abstraction that don't have predefined rules that we can't look into.
That's right. It's like inductive learning in action. Instead of following explicit rules like traditional software, machine learning models learn patterns and relationships from data. But since those patterns are encoded in internal parameters, it's tough to trace how decisions are made.
Exactly. And then there's also the statistical nature of machine learning models. Their outputs are probabilistic, they're random, and they're based on statistical inference, which means they can't always guarantee 100% accuracy. Plus, there's also no rule book to tweak or to fix errors, unlike what you have in traditional predefined systems following explicit rules.
And let's not forget the complexity of input spaces. With applications like image recognition or natural language processing, the relationships between inputs and outputs are so nonlinear and complicated that isolating the impact of single input is next to impossible.
Right, which is also why testing these systems is always such a challenge. Traditional methods, which depend on understanding a system's internal logic or peeking into the black box, so to speak, just don't cut it for black box models like these ML models.
So, how do we deal with this?
Yeah, that's an interesting question, and that is where this paper comes into play. Probabilistically extended ontologies, or peons, are a novel approach that are introduced in this paper. And peons provide a framework for testing machine learning models without needing to pry into their inner workings. We don't need to understand the system's internal logic in order to evaluate the models.
Okay, I'm intrigued. Uh, what exactly are probabilistically extended ontologies?
Yeah, I know it's a complicated word, so don't worry, I'll break it down for you. Ontologies are just like these formal blueprints of knowledge for a specific domain. They define everything that a certain problem can be or can have or consist of. They split everything down into classes, properties, and relationships. So classes are just entities or concepts like a person, a vehicle, the weather, and things like this. Properties are attributes of those classes. So, for example, a person can have attributes like age, they can have something like height, gender, and so on. Or the vehicle class can have attributes like speed, or size, or miles per gallon, and this type of thing. Now, relationships are things that connect different entities together. So, for example, we can connect the person class and the vehicle class by saying something like a person drives a vehicle. That's the relationship. Or rain is a type of weather. That's the relationship between these two classes of things. And that's
I,
how it is.
I got it. So, how do ontologies extend it into PONs?
Yeah, so peons just take it another step further by adding probability distributions over these partitions. So imagine we are testing a pedestrian detection system in a city. The ontology might partition the input data into distinct categories like pedestrians, vehicles, and weather. These are the different classes. And the pedestrian class can include things like children, adults, the elderly. Vehicles could be cars, trucks, bikes. Weather could be sunny, rainy, snowy. You get the idea. And the peons then assign probabilities to these partitions based on how likely it is that they're going to occur in real world scenarios. So, for example, An adult walking on a sunny day might be way more common than a child on a bike in the snow.
So it's not just organizing information, but also incorporating real-world likelihoods, is it?
Yeah, that's exactly it. So this approach lets you test machine learning models in a way that reflects the real-world distribution of scenarios. So in other words, it is a representative testing approach.
That's interesting. Does it help define when testing is complete?
Yeah, absolutely. Peons also help you calculate statistically significant sample sizes, giving clear end-of-test criteria. Plus, they also ensure fairness by letting you specify uniform distributions for sensitive attributes like gender or race and other things that may have an impact on testing.
That's a game changer for ethical testing. But how does this approach compare to traditional software testing?
Well, traditional software systems, they operate deductively. They follow explicit rules, almost as if they're following a rule book, which you can trace back. You test them with methods like n-wise testing, which checks for combinations of inputs, but that doesn't really work for machine learning systems because machine learning systems, by definition, are probabilistic and they're inductive, not deductive.
I see. So traditional testing isn't equipped to handle the randomness or the statistical nature of machine learning systems.
That's correct. And this paper even showed how n-wise testing fails. In one experiment on a machine learning object detection system, n-wise testing could not reproduce key quality criteria or align with the development process. So that just shows the failures of traditional systems in this machine learning context.
That's really a pretty clear limitation. What about the machine learning testing methods themselves?
Well, the machine learning based approaches offer several key advantages. First, they are able to handle the sheer complexity and the scale of modern ML systems. They can analyze massive data sets and generate a wide variety of diverse test cases when testing model performance.
That's huge for efficiency.
Definitely. And they're also adaptable. So as these systems evolve, the testing methods can also be adjusted to keep up. They're ripe for automation, meaning you don't even need a human being to sit behind the computer and to manage the testing for all of these ML models, meaning that everything can get faster and you can have more comprehensive testing cycles.
What about areas where traditional methods really struggle, like fairness or detecting subtle biases?
Yeah, that's another area where machine learning based testing also shines. This approach can analyze outputs across a wide variety of input ranges to uncover any hidden biases or inconsistencies that a human evaluator might glimpse over or fail to address. This testing approach also extends to testing non-functional requirements like the explainability of the outputs or the fairness or the robustness. So when we analyze a machine learning model's performance across many different scenarios or partitions, as we said, it helps us spot certain hidden biases that might not show up in the overall results when a human takes a look. So for example, if the model detects cyclists well during the day but struggles at night, at dusk, this could reveal a bias in how the model handles low light conditions. And we'd also look for unexpected behavior, like the model being inconsistent in certain scenarios, even if it is generally accurate overall. So by breaking down the performance across these specific partitions, we can uncover these issues and improve the model's reliability in all kinds of real-world conditions. And yeah, this is what these machine learning models do.
And it sounds like this could solve the oracle problem too. Traditional testing relies on having a precise expected output, which isn't always possible for machine learning systems.
Yeah, exactly. We don't really need an all-knowing, all-seeing perfect oracle in order to solve many of our problems. These ML-based testing focus on statistical behavior and deviations from expected patterns. So as long as it is a statistically significant output, then we're going to focus on it and we're going to be able to have a solution for it.
This is fascinating. It feels like probabilistically, uh, oh my gosh.
Extended ontologies.
Yes, that PEONs and
Yeah,
machine learning based testing are reshaping how we evaluate these systems.
I agree. They really are. And the paper also emphasized the ethical implications of these techniques because they ensure fairness and they help us avoid bias. Looking ahead, I think the authors of the paper wanted to develop tools for creating ontologies and using them to analyze weaknesses in existing machine learning systems.
It sounds like the future of testing is as innovative as the systems it's meant to validate.
Yeah, I couldn't have said it better myself. With frameworks like Peons, we're just getting closer and closer to building reliable ML systems that are effective, ethical, and also trustworthy.